It's Physics 141 online again. And here's an example problem that shows how to use the principle of conservation of energy to solve a simple mechanics problem. A spring of spring constant 120 newtons per meter rests on a horizontal frictionless surface. A block of 100 grams is used to compress the spring by an amount 15 centimeters. After the block is released, it slides up a frictionless slope. What is the maximum height the block reaches? And it should be pretty clear that this is a problem that we can most easily solve using conservation of energy. And that may take a while for you to be able to sort out in the problems that you're starting to work on now. But whenever we have problems that involve springs, that involve objects that change height, chances are real good that we're going to identify this as a problem that involves energy conservation, or at least where this is one of the best methods to use. There may be other ways to solve a problem like this, but we're going to try this first. And of course, then as we develop a plan for solving this, we need a sketch. We need a good sketch. And if you look at this carefully, you can see that there is a horizontal surface, and I will move it down a little bit, like this. And somehow there's going to be a slope involved, and I'll just draw it like this. On the horizontal surface, it tells us that there's a spring and that this block is going to compress the spring. So here I will draw in the equilibrium position for the spring, and this is where it would be if it was not compressed at all. So let me draw it like this and show that it's been compressed by this block of mass m. Okay, so there's the block, mass m, spring constant k. I usually like to draw a cursive k. I'm not sure why that is, but that's just the way I normally do it. And the amount that the block has been compressed, this x value here, is x equals, actually in this case, negative 15 centimeters, because x equals 0 is shown here. Stretching the spring would mean a positive x, compressing it would mean a negative value. And k and m are given in the problem. It says, though, after the block is released, it slides up a frictionless slope, and what's the maximum height it reaches? So I will try to just draw here in dotted lines an outline of a place up on the slope where the block reaches its maximum height. And we would like to find what that height is. And I'll call it h. It's not a given thing in the problem, it's what we're trying to solve for. All right, so that's the basic idea here. And if we then are using energy conservation, we'll write that equation down as we develop a plan for solving this. And the master equation that we use in all kinds of problems involving energy conservation looks like this. The initial kinetic energy plus the initial potential energy plus any work done by non-conservative forces is equal to the final kinetic energy added to the initial kinetic energy. That's our master equation. And what I would like you to do is get in the habit of writing out each of these terms separately and then plugging them into this equation. All right, so now we're going to make a list of each of these terms. The initial kinetic energy would be, of course, for the mass, 1/2 m the initial squared. As we look at the problem, though, we can see that the block is compressed, is used to compress the spring, and then it's released. And so if it's released, that means it's being released from rest. We're not giving it any kind of initial velocity. And so that should be 0. The initial potential energy, now in this problem there are two kinds of potential energy that we need to consider. There's the spring potential energy, and then there's the gravitational potential energy. All right, and the spring potential energy is 1/2 k x initial squared, and the gravitational potential energy is mg times y initial. I'm going to use y here because I've already got h in the problem. That's going to represent the final height. But gravitational potential energy is always measured in terms of the vertical position, so we'll just call it y initial. And we can work this out a little bit more in detail here, because 1/2 k x initial squared, that's basically the x initial is this negative 15 centimeters. So we'll just leave it like that. But y initial, if we measure height from the horizontal surface, if we measure y like that, then y initial will be 0, if that's where we're measuring from. Okay, so the y initial term drops out, and that makes the potential energy initial easier to write down. Work done by non-conservative forces, well, we were specifically told in this problem that there's no friction on the horizontal surface or on the slope, and so unless there's air resistance or something else acting, we will assume that the non-conservative work is 0. There are no non-conservative forces acting on the object. Okay, so now we want to write down the final kinetic energy and the final potential energy, and then we'll be set up to attempt the solution. Final kinetic energy, again, 1/2 mv final squared. But as I look at the problem carefully, if the block reaches its maximum height, it will do that right as it stops. And then, of course, if there's no friction on the slope, it'll slide back down again. But the maximum distance up the slope will be reached when it stops. So v final is equal to 0, and that makes this term go to 0. Final potential energy, okay, I will once again write down the two terms. We've got 1/2 k x final squared plus mg y final. We've got the spring and the gravitational potential energy. Now, what is x final? X final would be how much the spring is stretched or compressed. But when the object leaves the spring and it slides up the slope, the spring returns to its equilibrium position, right? Which would mean x final is equal to 0. So that term goes away. And what we can do with the gravitational potential energy is we can just substitute h for y final. So we write mg h. So now we've got all 5 terms that go into this equation, and we'll write it down. We're now in the evaluate step because we're ready to plug each of these values in to our master equation. So we evaluate this. We have the kinetic energy initial is 0. Initial potential energy, right, is 1/2 k x initial squared. And then no non-conservative work, so that's equal to, on the right-hand side, the final kinetic energy is 0. The final potential energy is mgh. So we started off with our master equation for conservation of energy, and it reduced to this. It actually turns out to be a fairly simple problem. And now we want to solve for h, so we'll divide both sides by mg and turn this around so that we can write h equals, and what's over here when we divide it by mg will be k x initial squared over twice mg. You can check the algebra there, but I believe that's correct. And if we're not provided any numbers, then this is our final answer. And we could go ahead and check to see whether the units for k and x and mg are correct for this to work out to be a height. But since we have numerical values, I'll do the unit calculations when I plug the numbers in, and we'll be able to check the units that way. Okay, so to evaluate with numbers, h then is, k is 120 newtons per meter. And this is what I mean about plugging in the units when you do the calculations. This is very important. X initial, 15 centimeters. Well, I want to convert that to meters. So I'm going to make it 0.15 meters, and that gets squared. And we divide now by 2 times the mass. The mass is 100 grams, and so that means 0.100 kilograms. I've converted it to kilograms because I know that's the standard mass unit. And then simply g, 9.8 meters per second squared. Okay, so when I crunch the numbers for that, I get 1.38 as a numerical value, but I can't just assume that it's necessarily meters. I've got to check these units out to see if they agree. And this is how I can catch mistakes. For example, if I forgot to square that 0.15 meters, I could work the units out and I would find out I didn't have meters. And that would give me a clue that I made a mistake somewhere. So let's go ahead and do this. Newtons per meter times meters squared. Well, one of the meters will cancel. So in the numerator, I will have Newton meters. All right. In the denominator, we just get kilograms meters per second squared. Kilograms meters per second squared. Now, what does that reduce to? Well, you might remember that a Newton, which is a force times an acceleration, is a kilogram meter per second squared. So the Newton term and what's in the denominator all cancels out. And so we're left with just 1.38 meters. So for the assess step, the very last thing that we do, we can say for sure that the units work out fine because we expect to get a distance. As far as the value, it's hard for us to say very much about it, but it does seem to be at least a plausible value. We don't know how stiff the spring is. Maybe 120 newtons per meter turns out to be a pretty stiff spring, so it launches the mass up the slope a fair distance, 1.38 meters. At least that seems reasonable. So that gives you a simple example for how to use the law of conservation of energy to solve a mechanics problem like this. I hope that's helpful. See you in class.